All right, let's get started. So thanks for coming today as well. Right, so I sent around an email this morning saying we're collecting university email address and your favorite email address and your matriculation number. So we need your university email address to distribute the evaluation sheets from the university. So we need that until Monday. And while doing that, you can also send us the favorite email address, because in some cases, we don't have your favorite email address and some of the important messages do not reach you. So this is a chance for you to tell us this, and also your matriculation number. We are going to need that at some point. So probably it's a good chance to collect that as well. Okay, and sorry for the short notice, because I only got the short notice from the university as well. So yeah, right. And then there's also going to be a tutorial today after the lecture with Alex there. So you can ask questions afterwards. So last time we talked about adversarial generalization. It's kind of a way to measure the worst case generalization for some model against a set of possible environments. So the adversary is finding the worst case environment for you, and you're kind of getting prepared against the worst case enemy. We looked into white box attacks in the pixel space, such as fast gradient sign method, or iterative methods such as PGD, projected gradient descent. And then we looked into other attack spaces or strategy spaces like physical attack spaces rather than digital space, or like shifting a bit of optical flow to generate new kinds of images. And then we also looked into black box attacks where you don't have access to the model details or the model parameters, but you can also always just query it, maybe with a few number of limitations for the number of queries. And then we also looked into one of the defense method, which is adversarial training, and that turns out to be quite effective in their experiments. Now, let's take a look at attack against those defenses. So we did some studies on attacks and then a bit on defenses, and then now we are on the attack side again against those defenses, right? So you can already see this kind of loop between attacks and defenses. So the year 2018 was a very loud year with a lot of attack methods and defense methods, and one side accusing the other side and so on. So the typical result is this ICML 2018 paper saying 7 out of 9 iClear 18 defenses do not work. And actually this ICML was only 3 months later than iClear conference. So they were super keen to just test out all the defenses from the previous conference and make this claim, right? And this is the central table they showed. So these are kind of defenses from iClear 18, and they show, of course, in their respective papers, they're going to say the accuracies are kind of preserved even after attack. But actually, with this ICML 18 attacks, you still get very low accuracy after the attack. So the defense is kind of not working. So in general, why was this happening, right? This was happening because if you look at those defenses, they're specifically targeted against gradient-based attacks, right? So the cheap way, very easy way to make the attacks not work again is by breaking down the gradients. You can just make the gradient malfunction. And then it's going to mislead gradient-based attacks altogether. But then the problem is the model itself is still vulnerable, even if those particular type of attacks are not working. Okay, so you can actually do a slight amount of modification on the attack algorithm to make it attack the model again. Okay, so we're going to look at examples of that. So this is kind of a schematic diagram of what's actually happening here. So we start from this original image X, and then let's say you kind of break down your gradient such that your PGD algorithm is not attacking the image in the right way, and eventually it results in this benign image, which is still recognized well. But the problem is there can still be some adversarial image within the neighborhood. Okay, so what we should keep in mind here is that the model being safe does not mean a gradient-based attack cannot find an attack. But the model being safe actually requires the total absence of any attack in the vicinity in the attack space. Okay. And if this is not guaranteed, then there can still be some algorithm that's going to find the attack. So let's take a look at example of input transformation-based defenses. So the basic idea is if you just transform your image in some different ways, ideally with some discrete transformations, which is not going to change the content of the image so much. And also, if you have a lot of variations of possible transformations, and then select one of them at random at test time, then that's probably going to be very effective against adversarial attacks. Because if you think about adversarial attacks, these are very small changes in the image, right? So if you're kind of killing all these small changes using, let's say, those transformations, then probably the attack is not working anymore. So one example of that is cropping and rescaling, right? For example, you just crop some part of the image containing the gist of what's going on in the image, and then rescale that to the input size for the network. Or you can do some bit depth reduction. So you're kind of killing some of the information, but ideally by doing this kind of denoising, you can also remove critical adversarial perturbations, okay? You can also do JPEG encoding and then decoding, right? This is kind of typical transformation that's kind of included in many of visual image viewer software on computers. So it's kind of natural way to defend against adversarial perturbations. And they also propose different ways, like remove some of the random pixels and then in-paint those removed pixels using TV, total variation in painting, or image quilting, meaning that you, instead of using the original image, you are taking some patches. You're rebuilding the image by using patches from other images that contain kind of a similar patch that you're looking for. So in a sense, you're doing some kind of collage. Right. So in a sense, you're doing this. Given input, you do transformation, and then there's safe input, and you give that to model, and ideally that leads to a correct prediction. And if you just measure the ability of FGSM and other attack methods of attacking these kind of images, you do have quite a bit of defense, level of defense. So here, this purple or pink line is no defense case. And this dotted line here is clean accuracy. So you see that after doing all these transformations here, your accuracy does not drop too much. So yeah, it looks like successful defense, it seems. But when you're attacking this kind of model as a white box, you actually also do have access to the transformations, right? So instead of just attacking the model, you attack the entire system, including the transformation itself. And then, for example, for cropping and rescaling, this is still linear and fully differentiable operation. And therefore, you can attack the whole part again. and generate successful attacks. Okay, so this is not working. This defense is not working. What about other discrete transformations, such as JPEG encoding and decoding? Okay, so here they can still generate. So if they just try to generate gradient here, it doesn't work because this is discrete transformation. But they can still generate gradients by just assuming that the forward pass was just identity mapping. Okay, then the gradient just goes through, and this is called straight through estimator. Yeah. And in terms of code, it looks like this. So forward pass is just doing JPEG encoding and then decoding, not differentiable, but this is still very close to identity mapping. But backwards, we do not take the gradient of JPEG encoding and decoding, but just as if the forward was identity mapping. So forward is like this, JPEG encode and then JPEG decode, but you're kind of overloading or like overwriting your backward function by just saying, given the backpropagation from the next layer, you just pass that through the previous layer, and that's it. Doesn't depend on the input value X either. Okay. Yeah, then and there's also this random mixture of transformations that people propose as a way to defend against white box models, because let's say when you do when there is some kind of uncertainty regarding what's going to be the transformation you're going to use for defending this model, then the white box becomes partially black box because you do not really know exactly what operation is taking place for this part. But even so, the attacker can still look at the possible list of transformations and generate an attack which works for any of these transformations. This is called expectation over transformations. So it looks like this. So instead of attacking a particular transformation T, you're attacking the expected output of your function over the possible transformations. And because gradient and expectations are linear, and also assuming the f is kind of smooth enough, then you can always swap integration and taking gradient. And therefore, you can take the individual gradients for each transformation and then average them, okay? So in terms of code, it looks like this. So let's say you want to generate expectation of a transformation attack. Then what you do is you randomly sample from the possible list of transformations. And then using that transformation, you generate gradient y here. Sorry, you first do forward pass, right? And then get y here, and then you generate the gradient grad x. And you're summing this grad x over multiple transformations to result in this grad EOT. And you add this grad EOT to this x to generate an attack. Well, here I didn't do any kind of gradient sign method or PGD here, but you can imagine how you can do those variants with EOT attacks, right? So this is kind of measuring, like this is pushing the limit for the capacity for the attacker. So if the attack has full capacity for addressing many possibilities for transformations at test time, then you can attack all of them at the same time. So given this figure from this original defense paper, it turns out that after this ICML 2018 attack, which applies all these techniques that I mentioned before, the accuracy still goes all the way down to 0%. So the defense is not working. One comment on adversarial training given by this paper is saying that even for this ICML 2018 paper, it was hard to attack adversarially trained models again with greater attack success rates. So that means adversarial training is still an effective defense, according to these people. Although it may still be possible that even after adversarial training, there may still be some adversarial attack within the L infinity or LP ball that's still adversarial to the model. But at least from the community perspective, I think adversarial training is still understood as a strong defense. The only caveat is that adversarial training is still very difficult to perform at scale. So if you're dealing with, let's say, ImageNet scale, then if someone did adversarial training at ImageNet scale, then I would be very impressed. Although it's possible. So now so we are talking about the capacity of the attacker and the defender, right? So adversary can still beat a lot of different possible transformations by generating the attack against all possible transformations, right? But what if the defender came up with even more number of transformations and did some random picking in this kind of, let's say, exponential number of possibilities, right? Can the attacker still attack against this kind of defender, right? You can see kind of the loop, right? There's attack and then defense, and it kind of continues. And this is the sequel after this EOT paper, which is barrage of random transformations. So they introduced these 10 different groups of possible image transformations, including color, precision, reduction, JPEG noise, swirl, noise injection, FFT perturbation, zoom, color space, contrast, grayscale, denoising. Not only that, with all these axes, they came up with all kinds of ways to randomly apply them in sequence, right? So that really generates an exponential number of possibilities here without changing the real content of the image. So even after doing all these kind of transformations, you can still, your model can still recognize the objects pretty well. But it's just that the sheer number of possibilities here makes it kind of hard for the attacker to prepare against all kinds of defenses. And this is the result. So on the right, you see the max adversary distance, epsilon, on the x-axis, and the accuracy after attack on the y-axis. And you see this BART, barrage of random transformations, with expectation over transformation 10. So they're already measuring the performance against expectation over transformation. So even after expectation over transformation, their claim is that the performance does not drop too much. So we can probably just look at top 1 here, and top 5 is kind of following the same trend as top 1, so we can just disregard that part. So if you just look at top 1, EOT 10 and 40, we still see that even after doing preparing against 10 different transformations or 40 different transformations, the attacker cannot push down the scores all the way down to 0. While, let's say if you did adversarial training is not as effective as barrage of random transformation here, right? Because the scores are actually going very close to 0, even after a very small adversarial distance. Okay. Yeah, this is it. So so BART is kind of a way to fight against EOT, but you can also imagine this kind of loop can go on forever. So that's the point I also kind of stopped following this field. Yeah.
You just said that adversarial training is not scalable yet. So this approach is even less scalable, right?
Well, but also you can in either case you can choose the level of scale that you wish to apply actually. So here you can also kind of control the list of the number k here to kind of yeah. And also for adversarial training, you can actually control the number of iterations per attack. So yeah, it's true. It's kind of hard to say for the entire family of method it's scalable or not scalable. But yeah, but also this is not like training either. So it's kind of a different type of compute that it's using, right? For training, there's zero cost for this one, but for inference, for every time you encounter a test sample, you need to apply k different transformations. So that's probably costly, but I also don't think these are as costly as like 1/4 pass, really, because these are also CPU implementable. So looks all right. So I wanted to kind of give you a little bit of summary of history of adversarial robustness in machine learning. So in 2014, there was a first attack, LBFGS, which I didn't talk about in this lecture because it's way too complicated and doesn't work too well. But there was a very simple attack, FGSM, afterwards, and it worked pretty well. And then 2016, you see a lot more attacks like deep fool and also black box attack. And then on the defense side, people looked into distillation as a possible defense. So I'm just giving you an idea of how the ideas flow here over years. And then in 2017, there was a strong attack and then a strong defense as well, adversarial training. And then people came up with detecting adversarial inputs. So instead of making your model stronger, you train a second model, which is just for detecting whether there is an adversarial pattern here or not. But then on the other side of the field, from the attack side, people also say, yeah, when you have such a detector, we can also generate a pattern that's avoiding these detections, right? If the detection method is also white box, right? So that's what they say here. And then there was a set of defenses from iClear 18. And then ICML 18 paper says they are not effective. And then afterwards, there's barrage of random transforms that came out, which says, yeah, even with this ICML 18 attack, we can defend against them. And then I kind of stopped following this field. And I thought this is a good example of dead end because you're kind of spiraling around attack and defense. It's like a cat and mouse game, right? So I looked into different alternatives here. One is, as I said, there's a strategy to just diversify your possibilities and randomize your choice among the possibilities. BART is a good case of that. But then this brings us into the question of whether the attacker or the defender has stronger or more capacity to generate attacks or defenses against the other side. And I think this is not very interesting for me. And then there were a lot of work on certified defenses afterwards, making sure that within this LP ball, there's absolutely no attack possible, okay? And then the third party was kind of, we should rather deal with realistic threats rather than this unrealistic worst case threats, okay? I'm gonna explain 2 and 3 briefly, and then that's the end of this part of the lecture. So what certified defenses people do is, for example, they have a lot of simplifying assumptions for the network or the adversarial objective or, yeah. So in this case, they simplify the network into a 2-layer neural network that looks like this, V and 6 it could be sigmoid or ReLU, and then Wx, where this sigmoid has to be non-linear and also has bounded gradients. And then we are going to write the worst case adversarial tag within this LP ball as A opt X. So A is the adversary, right? And then what they do in this paper is they create a sequence of upper bounds on a general attack A within the LP ball. And of course, when someone attacks this within this LP ball, it's still going to be better than when there's the worst case adversary, right? Which is A opt of X. And that is, so this paper later on bounds this worst case loss value with some kind of Lifshitz bound here, and then turns that Lifshitz bound here into some quadratic programming bound using the fact that this is just two-layer neural network. And then this is also bounded by some computable semi-definite programming with some dual formulation. I won't go into a lot of detail here, so I copied and pasted the same sequence of inequalities here. And then based on this final formulation, FSDP, they have formulated this loss function. So this is the typical kind of chain of thought for certified defense. So you first come up with a trainable objective. And then show that solving this trainable objective will make sure that there's no worse attack than certain type of attack, right? So for example, if you train with this objective, then you're going to get V, W, and this additional variable C. And these values will make sure that the output, the loss after any attack is bounded from above by this value here. It's going to be a not very tight bound anyways, or it requires probably very small value of epsilon to be tight. But still, it's meaningful in the sense that you get some certificate of defense, meaning that there's sure guarantee that whatever perturbation you have within this LP ball, your loss is only bounded to a certain level. Okay, so this is theoretically meaningful, but probably not so meaningful in practice yet. Also because you're kind of confining the studies to two-layer neural network yet. Okay. What about the other alternative, which is going towards less pessimistic defense? For example, defense against black box attacks is, I think, still very interesting subfield of adversarial perturbations, adversarial attacks. Or defense against non-adversarial, non-worst case perturbations are also interesting. And these are exactly what we have learned in the previous lectures, such as OOD generalization, domain generalization, cross-bias generalization. So I also see a lot of people that used to study adversarial perturbation are now spending their time on general OOD generalization and natural shifting distributions. Okay, so that's the end of the story for the adversarial generalization part. Yeah, the summary here is that DNNs are vulnerable within small LP ball. And if you follow these attacks and defenses, it tends to be a cat and mouse game. And so it seems very necessary that we should seek alternative directions from this research field. So that's it for the generalization bit. And now let's go to the explainability part of the lecture. So yeah, we're starting from a system now, which takes an input and gives you an output. So what happens if you understand the system very well? If you understand what's going on well, and if you're also understanding the underlying mechanisms very well, then you can use the system to control something. Or, for example, this is a kind of a diagram that people understand, economists understand. What's going to happen if you increase or decrease the policy rates, interest rates? Okay, so this is the decision by central banks. They can change the policy rates or purchase or sell assets, right? That's going to kind of control the amount of money in the market and affect a lot of different nodes here, such as money, the amount of money and credit, asset prices in general, stock prices, bond prices, bank rates, exchange rate with other countries. And then, yeah, a lot of chains here, right? And then eventually they wish to kind of control price, which is quite essential these days. But there's always a new situation coming, right? And if they encounter kind of new situation, they cannot simply rely on their experience, right? Because our lives are very limited, less than 100 years. And also, even if you look back in history, you don't have, we don't actually have so much history to really understand what we should do in those new situations that we are encountering in 21st century. So it's very important to know exactly what's happening in the system to do some control. And when we have a black box system that we do not understand, for example, then we do not exactly understand why, for example, a self-driving car is following the road in this case, but not following the road in the other case. So we don't have a very good control to fix this kind of system that's not working. So we have roughly two ways to control this kind of undefined behavior in out of distribution noble situations. First is to come up with an infinite list of unit tests and data augmentation, which is kind of what we're also looking into in the previous section, right? We can introduce a new kind of evaluation set every time, ImageNet A, B, C, D, right? These days. And then after introducing those kind of evaluation set, what is natural next step is to augment network training with exactly those samples. And then you're kind of sequentially conquering different unit tests, hoping that eventually it will lead to a strong system that's working well in any kind of situation. But the question is that going to happen, right? And the other way to go is first to understand and then fix it, right? So the evaluation in this case is not in terms of whether the model is working well in case ABC, but rather examining what kind of cues are used by the model, right? For example. And that's part of the explainability. So if you understand that the model is not utilizing the right kind of cue for making the recognition, then we have a way to control this, right? We can later on regularize the model to choose the cues that are generalizable. And I tend to believe that the second way of doing this is perhaps more scalable than the first way of doing that, right? Infinite number of unit tests are probably not going to solve all the problems. So explainability, in a sense, can be used for a lot of applications. For example, choosing the right features for fairness or demographic biases, or robustness to distribution shifts, or being able to control some large systems better, such as GPT-3 and large language models. For example, if you understand what GPT-3 does and knows, then probably we can quickly adapt those models to downstream tasks by only choosing the part of the model that are doing certain tasks, submodules that are doing certain tasks that are useful for the downstream task that I'm going to apply this model to. Okay, so there doesn't need to be any fine-tuning in that case. Or if you're using machine learning for science, then discovering this knowledge itself is the end goal, right? We need to understand what's happening in this scientific system. Instead of looking into the test data, we can also kind of reason back to the training data. For example, if your model seems to have learned something from your user data, something that is private to certain users, and certain users can even be identified because of this information hidden in the model, then it'd be very informative for the model developer to be able to trace back certain prediction back to the training data. So if let's say the large language model is outputting something that looks very close to someone's home address, right? Then being able to track down where this home address information came from in the training set is going to be very informative for those who are auditing training data and so on. And of course, there are also applications that require greater user trust when the human expert is working with machine learning system to generate better outcomes, such as finance, law, and medical applications these days. Okay, and yeah, this is kind of boring article from GDPR, but they are also setting out this rule, this philosophy of right to explanation. And nowadays, the explanation itself is kind of stipulated in some laws as well. Yeah. And then there's also explanation as, yeah, it's the same story, right? Data subjects right. If a machine learning system is making critical decisions based on some personal data, then the owner of the data, the person, has the right to require some explanation of which feature of my data has caused this this rejection of loan, for example. Yeah, and then these papers have identified 3 key barriers to transparency in general. So one is the most serious case when the company or let's say the bank here is intentionally concealing the decision procedure for their loan rejection, right? That's kind of intentional. And the second is even if the bank is kind of opening up everything to those people, the people may not be able to understand what's going on in the code, right? Because they do not understand Python language, for example. And third case is perhaps more interesting for our course, which is the mismatch between what is actually happening in this complex system and what is actually the capacity of human understanding. If you're showing all the internal weights of a model and so on to a human, then it's very unlikely that human will make some meaning out of that, right? So you need to do some kind of dimensionality reduction or some summarization of information and attachment of human understandable concepts to make sure this is actually communicated to humans. But there seems to be some kind of mismatch here. So that is sort of why we need explanation. But in general, let's try to characterize the situations when the explanation itself is needed. Some studies say explanations are required typically when something is not working. So when everything is working well, then we do not question why this is working or why is it so good. But when something is not working, then we raise questions, right? So the fact that explanation matters now, it means that there is some problem and that should be fixed using explanations. And it's also informative to see the cases when the explanation is not needed. So this paper comes up with these examples such as advertisement servers or postal code sorting, aircraft collision avoidance systems. Yeah, I don't fully agree with those examples yet, but because yeah, so the reasoning they have is there are no significant consequences for unacceptable results. Or the problem is sufficiently well studied and validated in real applications that we trust the system's decision, even if the system is not perfect. I think the reasoning is kind of good, but I think the examples are not good. Because I guess when postal code sorting, for example, goes wrong, then we're gonna inspect what went wrong in the process, for example. Or if the aircrafts collide, then of course there will be inspections of what went wrong and possibly fix the situation. I think this is a good example of actually when the explanation is needed. So let's try to define explainability. And before defining explainability, it's probably a good idea to start with a system that is deemed explainable. Or maybe we can resume in 5 minutes, okay? Because, yeah, it's been on 45 minutes already, so see you in 5 minutes. Okay, then let's get started with defining explainability. So maybe a good question that we can start the discussion with is, what is an explainable model to start from, right? And we have a good example of explainable system, which is sparse linear models. So let's say an output is composed of individual members of features, phi of I, right? And then there's some coefficient here. And let's say the number of features here is very small, right? Then this is called sparse linear model. And since we know like what is the components contributing factors to this sum very well, then we call this human understandable features. Okay, so that's a good example of explainable system. The other one is decision trees. So yeah, we can start from this root node, and then depending on certain features at a time, we are finding the children node here, and eventually reach the final decision of what kind of animal breed is that, right? And because all of the deciding features for the final decision follows some human understandable concept, we say this is, yeah, human interpretable. Unless there are so many different branches and so much depth and so on. If that's the case, then still it's probably very difficult for humans to understand. But for small decision trees, we say it's, yeah, human understandable. So given those two kind of examples of what is an explainable system, can we still define explainability? There's no easy answer to this. But even before defining explainability again, let's probably look into how humans explain to each other. Because that is also not so trivial, how humans are explaining to each other and what kind of explanation makes human happy. So for that, I based a lot of materials in this lecture on Tim Miller's paper. This is a really great paper that gives a perspective on the current explainable AI work from the social science perspective. So if you wish to work on this domain, then I highly recommend reading this paper. So as a starting point, we have a clear definition of explanation is an answer to why question, right? But this is not the end of the story. We first look into why do humans need explanation in the first place. First need is to find the meaning, because there seems to be some kind of contradiction and inconsistencies between the knowledge structure. And we are kind of trying to figure out at which point, at which kind of principle are we making contradictions or inconsistencies. Or there can be a kind of a contradiction between my understanding and the status quo in the outside world. And we probably wish to understand from which point is this contradiction coming. Or we need that for managing social interactions, to make sure that we are operating in the same kind of principle and we have a shared meaning, right? And ideally, we can also kind of influence someone else's actions by trying to understand each other, right? Why am I doing this and why you're doing that? And eventually, if I believe what you're doing is kind of have greater cause or have better kind of explanation, then I can also align my actions to what you're doing, for example. And this is not just for human-to-human explanations, but I think for human-to-AI system, this is very interesting and very important to find the meaning, like what this model is doing and why is this model not doing as I expect, and so on, and being able to trace back where this inconsistency is coming from, and also being able to kind of share our way of thinking with the machine's way of thinking. That's very critical to work with machine learning systems. So I'm gonna talk about a few characteristics of human-to-human explanations in general. So three critical aspects are: one, explanations are contrastive; two, they are selective; and three, they are social and context dependent and interactive. So what do I mean by contrastive explanations? We usually ask questions, for example, why did event P happen? But actually, in many cases, those kind of questions imply the second part of the question, which is instead of some other event Q. So even if the apparent format of your question is why A, it usually implies why A rather than B, for example. This other alternative possibility, which did not happen, is called foil, foil Q, right? And this is often implied. So to give you an example, why did Elizabeth open the door? There are many possible foils. For example, why did Elizabeth open the door rather than leave it closed? So this is a foil against this open, right? Why did Elizabeth open the door rather than the window? So that's the foil for the door. Why did Elizabeth open the door rather than Michael opening it? So that's the foil for Elizabeth. But to make a brief criticism of what explainable AI is working on, a lot of questions that are asked there are rather not having any foil in mind in general. So the typical question that is being asked is, why was this image categorized as A rather than, sorry, there's no rather than, right? And the argument that I'm trying to make here is probably it's better to ask questions like, why is this image categorized as A rather than B? So kind of making this foil clearer, right? So the other way to extend this question is, will this image still be categorized as A, even if the image is modified to something else, right? But actually, this kind of question is implied in many XAI questions as well. We're going to talk about that later in next week's lecture, actually. So in a sense, input gradients are also asking this kind of contrastive question. But I'm going to explain how that is so. Because apparently it doesn't look like asking for this contrastive explanation. The second ideal characteristic of a good explanation between humans is selective explanation. When someone asks for an explanation for some event, they're usually not asking for a full list of possible causes for the event, but only a very few important reasons or the causes that are kind of relevant to the discussion at hand, right? So we are very good those who are making explanations, they're very good at also selecting one or two key causes out of infinite number of causes, right? Because if we generate all kinds of causes for explaining this single event, then the causal chain can be too large and too hard to really handle for the explainee. So we need some kind of principle of simplicity here, and we should not overwhelm human users. So that's the other thing. And now social explanations. So there are a lot of studies from philosophy, psychology, and cognitive studies saying we are not just explaining the same thing to everyone, but we are actually changing the way we explain based on who we are talking to. Because eventually explanations are about transfer of knowledge rather than stating the fact and something that is just objective fact, but it's something subjective. If it turns out that the person who you're speaking to doesn't know something, then we are kind of filling in the gap in their understanding by explaining something. So in other words, the way we explain depends a lot on our model of the other person. If the other person seems to understand the subject very well and seems to be asking for something that is non-trivial as a cause of some event, then we can come up with even more complicated or something less obvious as a cause of an event, for example. But then if we look back on the XAI again, then we realize that there's actually very few work on these kind of interactive explanations yet. Because typically we generate explanations that are kind of human agnostic. We are generating explanations that should be working for everyone. But if you look into how humans interact and explain to each other, it looks like we should actually generate explanations that are personalized to explainee. So in other words, there should be some kind of interactive explanations. So through exchange of explanations and kind of confirmation of understanding, we can kind of continuously confirm that the other person is kind of understanding where I am and try to be on the same page for every kind of iteration. And then try to fill in the gap in the understanding as it goes. So actually, yeah, this video is quite popular, right? From Richard Feynman. And I also find it kind of hilarious because the interviewer is kind of asks a very naive question, and Richard Feynman is making fun of that, almost making fun of that, right? By saying almost suggesting that you're asking kind of wrong question by asking why, and then the interviewer goes very defensive and says, "Oh yeah, still, I think I'm asking the right question." And then Richard starts saying, "Well, actually, there is no single correct answer to why, and probably you should specify the context a bit more, and so on." But I think this video has a lot of interesting components of what this lecture is about, right? About the context dependency of explanations, and so on. So I recommend watching it, but I'm not going to turn it on now for the interest of time. But if you're interested, you can just watch it later on. Well, yeah. So now it's the same kind of question, right? How do we explain to each other? And now, what are good explanations, right? What are the conditions for good explanations? So here we are kind of trying to map what we have been talking about in terms of more refined terminologies that a lot of people in XAI field use. So there are terminologies like soundness, faithfulness, correctness, maybe simplicity, generality, relevance. Although simplicity, generality, relevance are not so often used in this field. So soundness here means your explanation should identify the true cause for an event. So if you're asking for some cause for something, like why did you recognize a bird in this image, right? And then if the model points to a feature which is not actually contributing to its prediction of bird, then you can say the model is not sound or not faithful. So it turns out to be a very critical criterion for a good explanation, because let's say you're a doctor and you wish to know why this your machine system has predicted an existence of cancer from some medical imaging. You wish to know what is the real thought process for the system, rather than the likely reasoning from human perspective, because by being able to really understand what's going on inside this machine, in its recognition mechanism, we can learn more than what humans are capable of extracting from this image, right? And so sometimes soundness can be at a trade-off relationship with the understandability of the explanations, or the alignment with your previous thought. But if you eventually wish to kind of understand new knowledge thanks to machine learning system, then what I think what you should be caring about is how sound the explanations are, and whether that's really truthful to what the machine is seeing in the input, or what's actually going on inside the machine. But what is also important is that this is not the only criterion for a good explanation. Because if you push too much for the soundness, then you can be citing all kinds of causes for explaining why this is happening, but that's going against the simplicity of your explanation. So you need a good balance between what is true and sound, and what is simple and can be handled by humans. Generality here means the way you generate your explanation should work for many other events. So the way you generate your explanation is only for a few specific kinds of events, then your explanation is not good. And finally, there's relevance, which is also very important. So this is asking the question of why do we need explanation at all, right? Do we need explanation to let's say fix some system, for example? Then a good explanation should be able to make you fix the system. If your explanation system is to make you understand better, then your explanation should make you understand better, whatever quantification you have for understanding better there is, right? So, because explanation can have different end goals, depending on the use case, you might want to align the quality of your explanation or the characteristic of your explanation to the final goal that you're going after. So yeah, now revisiting intrinsically explainable models, which are sparse linear model and decision trees. Now let's take a look at if they explain well. So let's go for soundness first. So do they actually explain the causes, the true causes, right? And the answer here is, by definition, yes, every feature is a sound cause for the outcome, right? For example, because every feature phi of I is actually contributing to the prediction of X, right? By by contributing the Ci phi of I factor to the summation. So sparse linear is actually contributing according to the feature importance. Simplicity is also held here because of the control over the number of features. That's why we needed sparsity here, because even if everything is linear, if we had billions of features, then you won't be able to understand what's happening here. The other factor is generality, right? Here, the way we explain is we are citing every phi I as the cause of the eventual outcome of X, right? And this way of explanation works for any kinds of feature phi of I in the feature space. So this explanation works by definition. And you can also generate contrastive explanations here by simulating contrastive reasoning ground up. So for example, we can measure the impact of, let's say, instead of having phi 1 to phi m different features, we can leave one of them out and still see what's going to happen afterwards. And that's going to be the counterfactual answer to what is the effect of removing one of the features out. And if we have this kind of linear system, then yeah, we can run the system twice and see what happens if you remove one of the features, for example. And this is also not social and interactive by default, because the kind of explanation that you get from this is not personalized, not taking your level of knowledge into account. But you can think of ways to attaching some chatbot or interactive system on top of this to make this possible again. And there's also relevance question. If the goal is to debug here, then yeah, you can also think of try to measure the quality of the explanation in terms of whether this is actually helping an actual human subject to clarify or find out the features that are not working well and being able to kind of fix that in the system. Okay. And now we go to some taxonomy of model explainability. There are different ways of dividing the set of explainability models, explainability methods. So the first axis is intrinsic explainability versus post-hoc explainability. And then there's global versus local. And finally, there's attributing to training samples versus test samples. Okay. So what do we mean by intrinsic versus post-hoc explainability? Intrinsic means the model itself is interpretable from the first place, meaning that it is sound, simple, and general by definition. And good examples are sparse linear models and decision trees. And post-hoc explainability means that the model is lacking in interpretability and one is trying to explain the behavior post-hoc. So a good example of post-hoc explainability is by trying to turn your neural network into a more interpretable system that has more intrinsic explainability. So yeah, so for example, this sparse linear model turns out to be very useful throughout our studies in explainability, because eventually what you do with deep neural network to explain it is by either turning a small part of your network into a sparse linear system and then analyze that sparse linear model, or you're kind of approximating the whole model using some sparse linear model, and then instead of looking into the entire system, you just explain this surrogate sparse linear model. So yeah, sparse linear model will come into play frequently in our lecture. And a bit more into the terminologies for explainability and interpretability. So according to their definition, Bieran and Cotton, interpretability is the degree to which an observer can understand the cause of a decision. And what is important is the distinction between interpretability and explanation. Explanation is post-hoc interpretability. So we can say a model is intrinsically interpretable. And then in that case, we don't need separate explanation. But let's say you have a deep neural network, which is not interpretable per se. And then you can generate an explanation post-hoc to make it interpretable again, for example. Okay. And then justification is any explanation why that explains why some decision is good, but it is not necessarily sound. So justification is any kind of explanation, which doesn't have to be sound. Yeah. So let's look into global versus local explainability as well. So a global explanation of a system means it's not a per case basis. For example, there's epidemics model such as SIR model, which looks into the transition of every individual from susceptible stage to infectious stage and then recovery stage. Okay, so based on this system of differential equations, we are able to kind of simulate what's going to happen if some people are infectious, the gamma rate here and beta rate here are at some levels, then we can make kind of predictions into the future. So in this case, we are not making a single understanding of a particular event, but we can kind of generate the trajectory of the whole for the whole time period, and also the whole SIR system here of how the curves behave. So this kind of global explainability is useful for understanding the global behavior of the system and scientific understanding, and later on, like simulating what is possible and what kind of future is going to happen given the current situation and so on, right? And that is actually not our primary interest in this lecture. Our interest in the lecture is more local explainability, which is focused on explaining why this particular case is happening. For example, why did my loan get rejected, right? And this kind of explanation is feasible even for deep networks. Right. And finally, there was a distinction between attribution to a training sample versus attribution to a test sample. Okay, so for telling you how to kind of distinguish the two, we can introduce the view of a model as a function of an input, right? So given input, it gives you output. But actually, your model itself is an output of your training data, right? Because given training data, you have a training algorithm, and the output of this training algorithm is a trained model, okay? And eventually, that trained model takes test input as an input and then gives you test output. So I like to write down the definition of a model or the prediction on a test sample, not just based on this single test input X, but also on this model parameter theta. And this model parameter theta is also dependent on the set of training data in the first place. So every prediction that your model is making is inherently an output of your test data and also your training data. So from this perspective, you can actually trace back the output for particular sample X to either one of the features in the test sample X, just X, right? Or you can also trace it back to a particular training sample in the training set. So depending on what's your kind of candidate space where you wish to attribute or blame your decision for this sample is, you may want to go back far back even into the training set. So we're gonna look into both training sample attribution and test sample attribution in this course. We're first gonna look at the test sample attribution. Okay, so that was it for the taxonomy of XAI techniques in general. And these are kind of final slides for the current status of XAI techniques in general. They are from those Kai's computer-human interaction, so human-computer interaction field, and they tend to be very critical about the development of XAI techniques in machine learning conferences and machine learning community, because they do not take humans into account too much. And as a result, despite there has been a lot of growth in XAI fields, when XAI techniques are actually used in practice, a lot of people actually found those techniques to be ineffective, potentially risky, and underused in real-world contexts. So I think it's very important at this stage to kind of condition our mindset to actually trying to help those who wish to use XAI techniques rather than working on techniques that looks fancy or that's kind of theoretically beautiful. And also, there has been criticism saying this field has been criticized for its technocritic view, where inmates are running the asylum, based on the impression that XAI researchers often develop explanations based on their own intuition, rather than the situation needs of their intended audience. So they're just building whatever looks fancy and nice and seems to be working in the real world without actually testing if it's actually helping people. And they frame this as solutionism and formalism, right? And I really wish to kind of move away from this kind of attitude of developing explainable AI techniques. And we as a group also really wish to kind of address the real challenges that people face and the real demands from those who actually need explainable AI systems. And I wish a lot of people try to do that as well in this field. So that's the last slide. So we have motivated the study of machine learning explainability. It's really needed these days because machine learning has a lot of problems and we have to fix them. And for fixing them, we need to understand the system. And machine learning explainability research is being criticized harshly for being useless. So what we have done in this lecture is to prepare ourselves to study machine learning explainability from this critical point of view, which is more human-centered and application-oriented. And so keeping all of this in mind, from next time, let's dive into machine learning explainability techniques. So yeah, I kind of stopped earlier than usual, but I think it's fine, right? So let's resume from the next topic next week.